We have Dr. Jin Akagi from OnChip, and the talk title is On-Chip Sort, Exploring the New Avenue of Sorting. Jin, you can go ahead and share your slides.
Great, okay. Well, thank you very much for the introduction. Can everyone hear?
Yes, we can.
So? Okay. All right, thank you. So on-chip sort, exploring the new avenue of sorting. So my name is Jin Akagi from OnChip Biotechnologies. OnChip is a company that's based in Tokyo, and I'm calling at 1 a.m. right now. So, you know, you may kind of hear me a bit sleepy a little bit, but I hope you don't really mind too much about that. Okay, well, moving on since I only have 25 minutes. Right. So we actually have two instruments in offer. But mainly today we'll be talking about this on-chip sort. It's our cell sorting system. And we have, it's a very unique system, and then I'd like to go through each point slowly and then so that make sure that everyone understands what's going on. So I usually say that we have three main advantages in using on-chip sort. And the first one being damage-free sorting. Here's a schematic of a conventional, what we call the conventional cell sorters, and that's pretty much the Jin method or qubit hybrid type of instruments. But we say that there are several damaging steps that's involved. For example, sorry, let me go ahead and get this to the spotlight so that everyone can see. Okay, so now you can see the laser beam over here. So you have a tube that contains a sample. The instrument sucks up the sample while the sheath from the sheath tank is being pushed into the qubit, and where we have hydrodynamic focusing going on. And obviously this is where the nozzle is, and then you apply ultrasonic waves to create and generate these droplets coming out of the nozzle. And then for those droplets that contains a cell of your interest, we zap it using electric charges, use electrostatic field to change its trajectory to collect the cells into a tube or into a plate. And then by doing so, there's several damaging steps that's involved. So for example, you apply high pressure to drive the sample, so cells experience high shear stress. And then you apply ultrasonic waves and electric charges to the cells so that cells are agitated to some extent. And at the very end, you have high-speed collision when you're collecting the cells. So all of these together, in the end, could potentially cause cell damage. But you know, like you probably don't sort of know how these cells actually feel. So I put it in a perspective where, you know, pretend that the cell is a the cell is a U, right? And then so the cell's experiencing a pressure as if you're diving 130 feet underwater. At the same time, you're crashing into a wall, or you know, to the say, for example, the side of the well plate, or into the liquid that's inside the tube at a speed of 55 miles per hour. That's fairly fast. So you know, you obviously would not be intact if you are, you know, flying in that speed and then all of a sudden colliding into a wall like that. So that's why, you know, we say that there are cell damages, and obviously it is clear to some extent for many of the users of the flow and cell sorters, just because, you know, some of the cells tend to die a little bit easier than the others, right? So, you know, I did say cell damage, but cell damage can be expressed in so many different ways. But what does damage mean, right? So I'll just say that the easiest and then the most common, well, I wouldn't say common, but I would say most obvious, it would be the cell death. And then often cells show slow or no cell growth. And also at the same time, morphological change and phenotypic changes could happen, and loss of function for the cells could happen. And occasionally RNA expression changes completely. So, so Peter Lopez, obviously from New York University, came up with an acronym 6 that stands for sorter-induced cellular stress, and then we use that quite a bit to explain this damage. Just try to go to the next place. So with the damage, because we all know that there's damage, we needed to do something different to overcome the stress or the damage to the cells. And then, so this is why we decided to incorporate a so-called disposable microfluidic chip. And I did not include a slide explaining what microfluidic is because I assume that everyone knows what it is by now. But by incorporating this at the very center, at the core of this technology, we have managed to get around a lot of things. So the principle of sorting using our sorter, we have a cartridge that's about the size of a credit card. And this is placed inside an instrument, and we have very narrow channels where you handle the liquid. And this is what happens. So let me just get the spotlights again. So at the top, you see the gray and red dots over here. These represent the cells. And these are the microfluidic channels where this liquid is flowing through. So what we do is we load the cell in this sample reservoir and we apply air pressure over the liquid to push the liquid through these microfluidic chips. And then we have sheath fluid coming through from the side where we have hydrodynamic focusing that's happening. And we use laser to detect every single cell that's passing through. For those cells that we do not want to sort, they simply travel straight down into our waste reservoir. But whenever we detect a cell of interest, we create a gentle liquid pulse from the side that pushes a cell to the collection reservoir. And by doing so, we have eliminated the damaging steps that I mentioned earlier. So the first one being low shear stress. We only apply 0.3 psi. So this is what the cells experience. And so it's a lot gentler when you compare to the other instruments where they use, for example, 20 to 40 psi, for example. And then also we don't need to create any of the droplet, or we don't need to apply electric charges. And also at the same time, because we use a gentle liquid pulse to shoot them across in a continuous flow of liquid, there's no high-speed collision that happens to the cells. So overall, it results in gentle sorting. Here's one of the examples, one of the very obvious examples where we have sorted nerve cells, neurons of rat fetal brain. And obviously, neurons are examples where they're very, very fragile. So, they often don't tend to survive after they've been sorted using a conventional sorter, which is depicted in the pictures at the very center. Pictures to the left, these are the cells that's been dissociated and then cultured over 7 days. So these are meant to be the healthy cells. And to the right, these are the cells that's been sorted using our sorter on-chip sort, and they look as if they've never been sorted. So this just kind of shows how gentle it is. At the same time, here's a few examples of eosinophil sorting. This has been compared using another conventional sorters as well. And then when they come out of the sorter, they sort of kind of end up bursting and then just loses this morphology completely. So we decided to quantify and quantitate that. So we have, using our sorting systems, this is the results from over 6 years ago. That's before I joined the company. So it's kind of outdated, but then still kind of shows pretty good results. Say, using our sorter, we can keep the cells in a good shape, maybe just about 70% of those in a good shape, and then maybe almost all the rest in half collapsed state. But these cells are so fragile that even pipetting up and down a few times will just burst these cells. So thinking about that, it's fairly good. A couple of those that out of 100 that we sorted were fully collapsed. But using another conventional sorter, using at the most gentle condition, you sort of see less than half of those being kept in a good shape. So it's just it's a comparison that you can kind of make. Here's an example of the changes that happens that's being observed on gene expressions. So these are the Hela cells that's being sorted using our sorter and then also the conventional sorter in a bulk, and then being put it into the bulk microarray to see what kind of RNA expressions have been observed overall, as a overall meaning as a bulk. When these cells are sorted using the conventional sorter, upregulation of these gene expressions was about 1.24%, whereas downregulation was 5.86%. Doesn't seem that overly big, but do remember that this is a bulk microarray, so it is the averaged out gene upregulation and downregulation. And then compared to that, using our sorter, we have kind of reduced the amount of upregulation and downregulation quite significantly. So thinking about that, when you're talking about, for example, down into the single cell level, these become more obvious. Where people who want to do single cell RNA-seq, for example, these are extremely important. I did talk about cells that were in singles and in individual cells, but then we can also sort something that's really, really large. Here's an example of cell spheroid sorting. So cell spheroids are 3D spherical clusters. And people tend to use those because they're better representation of organs and tissues than single cells. But when you culture them, they tend to be they tend to grow in a very different rate. So you end up having various sizes. So one of the things that we tried to do is not based on any fluorescence in this case, but just based on the forward scatter and also side scatter, we decided to sort out a spheroid that's roughly about 100 micrometers or 110 micrometers. And then so now from varying sizes, we managed to get monodisperse cell spheroids out from these samples. So as you can see from the plot on the right. I did talk about cell clusters, but it doesn't have to be cell clusters. It can be something that's larger than standard cells. So these are the protozoa that lives in the gut of termites. So there's a researcher that they just extracted these protozoa out of these gut, and then hey, there's so many of these protozoa, and there's these big guys and small ones and tiny dot ones. These are all living creatures that's inside. And then so they decided that they wanted to sort something big this time around. And then so by sorting, we can keep those cells, keep these protozoa nicely in shape. So if you put these big ones like the clusters and also protozoa and other living organisms that's fairly big, through a conventional sorting system, they tend to sort of get tortured and ripped apart and just come out dead a lot of the times. But because our sorting system is nice and general, even when they're so big, we can still sort them without just hindering the viability. I did talk about something big just now, but we do some smaller clusters too. For example, in this case, you can see blue and red and green dots on the left. So these each represent different types of different cell types. But for those red and green cells, they like to stick with each other. So what we have decided to do is just let them sort of form a cell complex, and it's sorted for double positives so that we can get those double positives out. And then, as you can see, we actually can sort them without breaking these bonds apart. Whereas those bonds are so weak that even pipetting up and down a few times will just simply easily dissociate those cells, paired cells. So this shows how nice and gentle it is once again. We have a lot of things going on. So it can be cell spheroids, but also things like the cell, like small bits of tissues that's being dissected out from from mice, for example. People do sorting of organoids and eggs that reaches up to about 110 microns also, and also some long cells or even single cells that's really, really large. We can do a lot of different things. So that was the first advantage, damage-free sorting. I did talk about something that I did forget to mention is that we can sort something from 0.5 microns up to 150 microns. So that's a range that we can play with. Okay, Going to the second advantage of being sterile and cross-contamination free. What does that mean? Our cell sorter on-chip sort is actually a lot smaller than this other standard cell sorting system. I did put FACS-ARIA 3 here just for the sake of the comparison, but it is a lot smaller, so it is small enough to easily fit inside a biosafety cabinet, and therefore people would like to handle cells and samples in a clean hood as a biosafety cabinet to ensure that everything's nice and sterile, for example. And then we have since our instrument runs everything in disposable microfluidic chips, all of entire fluidics is fixed inside these chips over here, which is exchangeable as well. So by discarding this chip, you're pretty much exchanging the whole fluidics, and therefore there will never be any sort of cross-contamination between samples. At the same time, these chips are made in a clean room, and then also we also have a special sterilization method so that you can be ensured that there won't be any contaminants, for example. And then by operating everything inside a biosafety cabinet, you can ensure that everything is perfectly clean. Then the third advantage, broad selection of sheath fluid. Our instrument, once again, at the very beginning, I explained how we don't need any of these electric charging and so on. For that reason, we can actually, well, as a user, you get to choose whatever the media you like to use to run. So whatever the sheath fluid you like to use. So people tend to use culture medium that's right for the cells that people are sorting, so that the cells will be happy at the until the very end of the sort. And then people often use isotonic solutions, seawater for marine organisms, fresh water for things like algae, and then even oil. Yeah, so it is really much up to you. The only liquid that we have had problems are organic solvents, because it just simply dissolves the plastic of the microfluidic chip. Here's an example. So our instrument has been traveling around the ocean on one of these vessels, research vessels, and they traveled all the way from Tokyo to the, or more like Japan, to the coast of Indonesia, where they actually, at the spot, collect the seawater and phytoplanktons, and then just sort using the seawater that's been filtered at the spot. And then, and these samples need to be taken fresh, sorted fresh, and then preserved for later to do nitrogen and carbon isotoping. So things like that we can do. And then, how the ship sort of toppled around, and then, just it's never horizontal. That's okay, because we don't spit any of these droplets out of the nozzle. Everything is handled within the microfluidic chip. So even if it was tilted to some extent, we can still sort everything fine. Another example is talking about sorting of emulsion droplets. And emulsion droplets, so for those people who are not too familiar with it, it's liquid droplets that's suspended in oil. And then so these can act as a vessel, just like a reaction vessel. The size tend to range from about, people typically use droplets of between somewhere between 20 to about 150 of those. And then what they can do is just simply trap cells or trap single nucleotide or whatever they like to trap, they can actually do. And then if you'd like to carry out, for example, 1 million reactions on a 384 well plate, you would need 2,604 of these well plates. And it would just cost a lot and takes a lot of time handling them, and it also takes a lot of space. But this 1 million reactions or reactors, because these are droplets, can fit inside a standard 1.5 mil Eppendorf tube. What people tend to do with it is just to carry out some kind of reactions inside, obviously. But what people have done is, in this example, they've just captured them in the bacteria using this FRET-based RNA probe. And then for those droplets that contain the bacteria and that has successfully they multiplied and cultured, they just show off the green fluorescence. So we can actually detect and sort those droplets using our sorting system using oil as sheath fluid. And so it's something that it's relatively new to a lot of the people, and then and then it has been a popular topic in Japan for a while. So yeah, it's been a very good application for us as well, using and just a one of the example of freedom of using sheath fluid. So when you actually under the microscope, this is how it looks like before sorting. So it's one positive droplet, and it's a second positive droplets. And then when you actually sort them, you can actually sort everything that's in pretty nice high purity as well. Here's another example of capturing, these are Tetrahymena, so these are the things that lives in the pond that swim around. You can capture them, culture them. For those droplets that contains these multiplied Tetrahymena, you can actually sort them. I don't know if any answer is actively moving. And then we can also do things like the hydrogel ball sorting that's suspended in either aqueous solution or in oil. We can do things like that. So that hydrogel balls are like just like emulsion droplets, but they somewhat more you can actually perfuse through media inside the droplet as well. Things like that we can actually do. Anything that's up to 150 micrometers. So other reasons why people choose on-chip sort over the other sorters. One of the very good thing is that there are many new and then many users who are not familiar with flow actually come and talk to us because it is a very easy instrument to use. For one of the reason being no calibration required. So we don't need any of these time droplet delay type of calibration, just because we set the parameters to accommodate for slight changes day to day or depending on what kind of media you use. So we just cover a lot of the things for the users. And then also, for those people who are not familiar, they often sort of mess things up. But actually, we don't actually waste any of the precious sample because all that unsorted portion of the things would be accumulated on the chip. So we can recover them and run again. And we are also particularly good at sorting rare cells as well. So these are, that's for many reasons. For one thing, we can do so-called multi-step sorting. And then we have minimal sample volume requirement of only 20 microliters. And there's no cell loss due to our special media that reduces the risk of cell adhesion and hardly any dead volume. And also at the same time, once again, waste recovery. So I did talk about the damage-free multi-step sorting just now. What you do is you actually sort those target cells that's extremely, extremely concentrated. So they, like each one of these pulses would end up collecting some of the unwanted cells, but it's okay. You can sort them and then take out what's being collected, resort it again, do it multiple times so you can actually enrich for these extremely, extremely rare cells. So here's an example. We have so-called the circulating tumor cell example where CTCs, you can actually find only about, say, 5 cells and 4 milliliters of blood. And that's, and then they're sort of, floating around with tons of white blood cells as well. But we can actually, by doing these sorting steps, you can actually enrich them without losing those cells. So that's something that we're good at doing. So here we have a number, from the 4 milliliters of peripheral blood, we on purposely spiked in a known number of cells, and then so how many actually we ended up recovering? We tend to recover about, say, 80% of those cells back, so it's pretty good. Just basic specifications. We have 3. We can install up to 3 lasers from option of 4 different lasers. We can detect forward and side scatter, which is pretty unique for a microfluidic chip. Others cannot often measure both of forward and side scatter. And then we can detect up to 6 fluorescent colors. Here's just the spec sheet. It's just for your reference, but we can, at the sorting rate, we have a sorting rate that's a lot slower than conventional sorters, but we can collect at a rate of 1,000 cells per second. So once again, it is slower, but in most cases, people are satisfied. A lot of our customers come up and say, hey, it's not too. So that was all for me. I think I may have just gone through about 25 minutes. So the rest, I think I'll leave it for the questions. So thank you very much. Something that I did forget to mention is that right now, because due to the coronavirus, we cannot really sort of start it just yet, but we just recently got an office in the US. So we will be based in the US once this whole corona thing goes away. And then so hope to see everyone, locally, really. You probably see me around in a lot of different shows and places. So thank you very much.
Thank you so much, Jin. That was absolutely wonderful. And it's always a pleasure seeing you at the meetings, and you've always been so helpful.
Well, thank you so much. Yeah.
And we actually have a couple of questions now, and you ended with a good amount of time. We're 4 minutes for questions, so it's perfect. Yeah. Ben Daniel is asking, have you compared true jet and air systems such as the MoFlow to your on-chip system, or has it only been cuvette-based systems?
Right, so I did compare, I don't want to actually name all of them, but we have done comparison with MoFlow. And MoFlow tends to be a little bit gentler, but we still saw a bit of a difference. I didn't have a good data to show this time around. But we also did compare things with, I'll just name it. But just for example, Sony SH800, I believe, and the Fax Aria, and several others too. And not quite, and we haven't done too many comparisons yet for other microfluidic chip sorters. Just haven't had that much of an opportunity, but we have been doing so slowly.
Okay, great. And then Lydia Tessa is asking, I think from one of the slides about midway through, how do you differentiate green-red complex from aggregates? So do you have, I'm going to add on to that, do you have like a doublet exclusion capability?
Yeah, so we can, for example, do, exactly double discrimination, but actually, no, you shouldn't be doing that because it would eliminate all the green-red complex as well. So what we have simply done is just so aggregates, meaning they're attached to each other. That's we won't be able to tell the difference actually if they're attached together. But yeah, that's the only answer I could give at this moment.
Okay, sounds good. Ben has another question. He's asking if you or maybe anyone else has tried sorting any cells that have utilized the microbubble technology.
Actually, no, we've never done so. These microbubbles, they're the one that is it the one that just attached to the cells and float?
Yes. Yep.
Yes. No, we haven't done that yet. Something that it does float actually though is the emulsion droplets, and then so what we do is simply run the suspending liquid first, and then all those cells or the droplets would sort of start to run at the very end of the whole liquid, and then we can do something like that. So I believe these microbubbles can be sorted as well.
Okay, great. And then I'm actually going to combine a question from Ira with a question that I have as well. So we'll make it a two-parter, and we have 1 minute left. So I was curious if you have any automatic clog detection tools on the sorter that would detect if there was a large aggregate that might be causing some impurities. And then another question from Ira is there also any temperature control on the unit?
Okay, so starting with a temperature control, no, unfortunately we don't have a temperature control at this moment, but this is something that we are keen to add as well. People are extremely worried about the temperature, but we don't seem to have too much of a problem so far for several reasons, because we can keep the chip holder reagent nice and cold or warm, depending on the cell type. And answering about the clogs, we see the event rates go down when there is a true clog, but we usually don't see too much of a clog because the channel width is a lot wider than, it's a completely different concept to the nozzles. So we have two different types of channel width of 80 and 150, and then we can just utilize the whole width of that. And then so unless there's something huge and gunky that comes and then clogs it, you don't hardly ever see them. Even if you do see them, you sort of detect them by the change in event rate. At the same time, we also have a CCD camera that is constantly looking at the channel. And so you can actually check if it is indeed clogged. And then we do have a declog method that's easily done on the software too.
Perfect. Thank you so much, Jin. Those are all the questions that we have, and we're right on time. So I want to say thank you again for a really wonderful talk and for joining us at midnight.
So, thank you very much.
Thank you.